until or maybe still online class. 15 October still online class, and probably this will be physical. Okay, but it's still in my plan, so maybe it can be changed. Okay, but hopefully we can have physical class. I will ask one more time later in the feedback time whether you want to have physical class early or maybe later. That's also okay. That's also fine. So we can have physical class uh, anytime actually. But I want to finish the chapter 2 first, all okay, because I have started the class chapter 1, chapter 2 online. So I will finish the online, all the things, and then chapter 3 maybe physical class. Okay. 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 I hope you don't mind for Friday because we start at 8:10 and we don't have any break. So actually we can finish maybe 9 around 9:50 we can finish actually. Okay, let me start and we can go to the what we have done uh, last feedback. So this is the question. Okay. Oh, the link is okay. I will put in the Google Classroom later. The link is already in, I think, in the Moodle. Oh, wait. Wait a moment. Okay. Let's start with some review. Okay, I think you get correct here. It's the B C, and D. You can check the answer one by one. So if you look here, you have this is the asymptote should be equal to not 1, it should be 2, right? And number E, limit of the function x approaching 2. X approaching 2 is here. So it should be going down here, right? So it should be negative. And asymptote will be s equals 0. This is 0. 0 and 2 is okay. And negative 1 is here. And it should be y equal 2. Okay? That's why this is correct here. Okay. Okay. The other is, okay, this is, I think, important to mention. You have f and g. Okay? And by definition, at the first, the limit as x approaching 0 of f is going to have infinity. G also having infinity. So the question is asking whether you have limit as x approaching 0 of f and g, is it going to have 0? Or for example, let's say this is x. Okay? Let's say f of x is x and g of x is x squared. Wait, I think it's better to have 1 over x squared, 1 over x4. Okay. This will be this, right? And this will be this. And this term here is not 0. So we cannot do this, okay? Why? Because this is a concept, an abstract, okay? Am I right? This is not a number. So that's why it's false, okay? Okay, let's start. I will do some a little bit review, okay, about the chapter, especially the continuity. So let me give you the questions here. I hope you can read it. Find the numbers of which f is discontinued, at which of this number is f continuous from right, from left, or neither. Actually, the important question is we need to find at which the numbers when the function is discontinued. Okay, that's the initial question. Okay, so you can try for a few minutes. And if you can also draw the graph if you want. And meanwhile, please join the Google Classroom. Okay, there's only 35 students in the Google Classroom. Okay. Please join because sometimes I give you some assignment. Sometimes the assignment is based on like you write on paper, you photo, and then you send it uh, through the Google Classroom. Sometimes I'm giving you a quiz platform from the Google Classroom, and then you need uh, to work it. And maybe the time is just 10 minutes. So when you open the platform, you'll have 10 minutes to fill in the form. Sometimes I will give you that kind of assignment. So please join the Google Classroom. Okay. If not, then you will not be able to join the activity. And to join the Google Classroom, you need to use your GApps account. Okay. Okay. Let me uh, going into detail for the question. Um, so if you look, this function here is piecewise defined functions. Okay. We look here and we see that from the function itself, okay, we have three equation here, right? Uh, I will write f is continuous. At least from the beginning, we know that from negative infinity to 0, it will be continuous. Okay, and we can also write since it is uh, a polynomial or linear equations. Okay, this is polynomial degree 1. It's linear, and then continuous on 0, 1. Or maybe I will combine this with this because it's both are polynomial, and f is continuous on 0, 1 because it is exponential e to the x here, right? If you are maybe not remember what is e, or you don't know what is e is stated for Euler number. It's one of the irrational number. The number is around 2.7, and it will have a long decimals like that. Okay. Okay. Now to check discontinuity, we can look at the limit. Okay. We can look at the limit for 0 and 1. Okay. So first we go to limit as x approaching 0. So we can check limit as x approaching 0, and we can check the one side limit. So 0 from the left, and we can write 0 from the left is this one, right? So we can check this x plus 2. Okay. And we can substitute and becomes 2. And we can check also at 0 from the right. And this will be e to the x. And it will be 1. E with the power of 0 is 1. Okay. So we will see here, we observe that it's not equal, right? So we can say that limit x approaching 0 does not exist. So we have a discontinuity on discontinuity at x equals 0. Okay. Okay. And also we can observe the x approaching 1. So we can check limit as x approaching 1 from the left. Okay. This is becoming e. Okay. And limit as x approaching 1 from the right. This is 1. And it's still discontinue, right? Still discontinue. So limit is not exist. And we agree that discontinuity at x equal 1. Okay, but we still have some continuity. Okay, we can uh, we can draw if you want to look at more detail. This is one. Uh, let's say this is the E. Okay. Let's say this is one. This is one E, and also we have this is two. Maybe two is around here. Two. And this is having an open interval. Okay. So probably this is our graph like this. Okay. But from here, we can see also, if you look here, we have at here, f is continuous, right? Continuous, let's say from the left at x equal 1. Okay. So it's continuous from here to here, right? And you can check here. It's true. Okay. Okay. E. Can you explain again how you got E? E. Here. What do you mean, Helen? I don't get your point. Your question. E is from the function itself, and E with the power of 1 is E. Okay. Do you get it? Huh? What do you mean? Not real value? It's a real value. What do you mean not real value? E is irrational, but it's real numbers. Yes, just like pi. You actually why it's called irrational numbers, okay? Because the decimals here, okay? Yeah, this is not the same as e. E is and a lot of decimals here. Okay? Drawing the graph. You just put here. You just put all the linear, exponential, and yeah, the x plus 2 and 2 minus x is linear. Oh yeah, thank you. You can check the Wikipedia. Okay, thank you for sharing the link. Okay, I think how to draw the graph for linear and e. Uh, I think I cannot explain in this calculus course because it's more related to basic of math. So I think you can check basic of math to see the drawing for the graphs. Okay, how to draw. Okay, but for the e, okay, I will explain for the e. Okay, so e is irrational number. Okay, irrational number means you have a decimals, but you cannot put your decimals into a fractions. Why? Because the decimals is never stopped. Like pi, you have 3, but it's not 3.14, right? It's long numbers. And maybe there is also like if you read some findings in mathematics, there is a topics like how many decimals of pi we can find until now. And maybe every year or every 2 years, it can be changed. Like maybe you can find maybe we have like 20, and maybe the other mathematicians they find, oh, it's actually 21. Oh, it's actually 22, and it can be changed. Right? Okay, it can be changed. It can be add. It can be add, and it make a long decimals. Okay, and this pi is actually the same case with e. Okay, so you cannot have the exact decimals like this. It should be having more decimals here, maybe 2 or blah 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 blah, blah like that, like that. Okay, I hope you get my point, Helen. That's why it's called irrational number. Okay. E. Okay. It's actually interesting if you try to find, and maybe there's some videos on YouTube about the irrational numbers, about e, about pi, and that is actually quite interesting. Okay. Okay. One more thing about drawing. Okay, Jordan, if you want to learn more, okay, you can draw one by one. X plus 2, 2 minus x. You can draw uh, maybe the one here, and the other one is this, right? And then you cut based on the interval, okay? And maybe in the other graph, you draw the e. This is e, and then you cut based on the interval. Maybe here to here, you cut, okay? So you are only using this part, okay? And this is also you cut here, you cut here. Depends on the interval, okay? That's how you draw the graph. Okay? But if you are confused how to draw, you can draw one by one and then cut based on the interval. Okay. Yes, you can also use the table to see the value. So you can check, like for example, the x is from 1, 0, 2, and then you can check the functions here, and you can check one by one when the function is 2 minus x, when the function is e to the x, and then when the function is x plus 2, you can plot the uh, plot the point, and then you can find uh, which is the value for the function. Okay. 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 Next question. I think. Any questions again? Okay. Next questions. For what value of the constant c is the function f continuous on all real numbers or all intervals? Okay. This means all real numbers or all x values. Okay, and you have a piecewise cx squared. Okay, and this is maybe it's not, so it's x cubed. Okay, so cx squared plus 2x when the interval is x less than 2, and then x cubed minus cx when x is greater or equal to. Okay, let me give you a few minutes to try this. Okay, so it's actually asking what is c, right? What is c? Okay, if you don't understand the question. So for what value of the constant c is the function f is continuous? So what is c? The requirement is f is continuous. Okay, you can try first. Yeah, 2/3. Correct, correct. Good, good. Okay. Um, so I think to start with the questions, yeah, to start with the questions, okay, first we can think of the continuous functions. Okay? Continuous function, it has some requirement to be for our functions to be continuous. Okay? So functions is continuous if, okay, limit as x, let me write the general terms, is equal with the, so left hand limit equal right hand limit, and also let me write this is L and this is also L. So these two requirements makes the limit continuous. So let's start with the equaling the limit. Okay, so limit for 2, right? We can evaluate limit as x approaching 2. Okay, so limit as x so x approaching 2 from the left, we can put the cx squared plus 2x, and then we get direct substitution. So it's 4c plus 4, right? And the right side, we have x cubed minus cx. We get 8 minus 2c. Okay, and we need to have this equal value. So we get c is actually 2/3, and it doesn't have any requirement to like additional questions. So we just need to find c. So after you find the c, then that is your answer. Okay. Okay. Let me check. Okay, let us continue. This is the 2.6. Okay, still 2.6. I think we already discussed the limits at infinity, right? Here, this is what we have done here. Limits at infinity, horizontal asymptote. Okay, we already discussed this. We also discussed the tangent inverse and so on. Okay. Okay. Now there's a subsection still in 2.6. Still is limits at infinity, but it's called infinite limit at infinity. Okay. The notations is limit as x approaching infinity of the function f equal infinity. So the result will be infinity. You can check the limit as x approaching infinity of x cubed. This will be infinity. If you look at the graph, let me check whether I got the limit of infinity or not. Let me check. Okay, I got the picture now. Okay. So if you look here, okay, when you are going to have an infinite amount as x approaching infinity, right? The value of f is also getting infinite, right? Okay. The same or similar when you are going to the left, you're also going to have an infinite amount. Let me write here. When you're also going to the left, you also have a negatively large value. Okay. We also can argue and also compare the x cubed with the, let me check, with the exponential, okay, the e. Okay, and remember, because e to the x and also ln x, the log part, that is among one of the functions that appears in calculus. So it will be, you will see the functions very, very often. Okay, so it's better remember how it looks like. Okay, the e to the x, and also you need to also remember ln x, which means this is the inverse. Okay. Okay, now look at the what I want you to look at is you need to see the x cubed, okay, and e to the x. Okay, so let me get you to the this point here, okay, and this point here. Okay, this is a intersection of two curve. Okay, so first probably you will see that here of course, E is higher than the x cube, because e to the x is never reached zero, right? E to the x never reached zero. It's closer to zero but never reached zero. When the x cube, it can be zero, so it's also it's going to be here. Okay? But from here to here, if you look at the graph, the x cube is higher than the e to the x. Okay, but then after some point here, you can find the point if you want and look for solutions. I will leave that to you. Okay? So when you reach here, this point here, the e to the x is getting larger and x cubed, and eventually you see the gap here is getting bigger, right? One conclusion that I can give to you is exponential is really, really significant when you increase the x. So exponential is increasing faster than polynomial. Okay, and using this image like a curve visualized in your mind, sometimes it helps you to understand some questions in calculus. Okay? And sometimes when you cannot solve the questions in equation, maybe you can solve by graph. Okay? And then you can just use your logic and write down how you can get the results like that. Okay. Okay, and for the e, if you get the limit, okay, as uh, as x approaching infinity of e is going to have an infinite. Okay? But it's the same as x cubed. Okay, it's the same as x cubed. But at some point, okay, you can make a conclusion that the e to the x, okay, e to the x here is faster than x cubed. Okay, faster than x cubed. And remember also, when you have x approaching negative infinity of e to the x, this will be 0. Okay, because it's going to be here. Okay. So this is x going to be approaching negative infinity. It's getting 0 here. And when you are using some another point of view, you can also, for example, like that. This is actually similar. Actually similar. Okay. To solve this, actually we can do some substitutions. Okay? We can let the maybe t. Okay, maybe t is equal 1 over x, and we can imagine that when x is going to be approaching 0 from the left, t is getting closer to negative, right? If you don't remember the e to the x, you can draw the e to the x. Okay, so let me use different color. So this is going x going to the 0 from the left, and it's going down, right? So it's going to the negative infinity. Okay, this is y equal 1 over x. Okay, now from here we can put in to our limit. So limit as t. Now we are changing to another variable t to negative infinity, and then e, and then t. And this is precisely the same as this. And we can simplify that this is also equal 0. Okay. 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 How to prove it by using the definition of limit. Which one? Definition of limit. Oh, Stephen, which one the definition of limit? What do you want? What do you mean? Actually, this case here is already a definition by itself. Okay, so we can have this. Okay, at uh, some cases here, and we can also have at least several cases. Okay, at least this four. Okay. So we can use this form here to show or to indicate the f of x become large as x become large. Okay. Okay. I think that is the the, uh, the concept. Okay. So basically, infinity limit at infinity is uh, one concept that might happen in a function, that when you are going to have x or increasing x as large as possible, you can find that the functions is also increasing larger and larger, and it will not getting any L. Okay. If you look at the definition of limit, at the very beginning we have the limit. Uh, let me write here. Usual limit, you have limit x approaching a, f of x, and it's L, right? Okay, that's the idea of definition of limit at the very beginning of our class, right? But then, in some cases, it's not always the case. We can have x getting larger, and the functions is the value is also getting larger. So it's a phenomenon that might happen. Okay. Okay. Now, okay. Uh, Let me give you another idea to think. Okay, to think. Uh, if we have this limit, okay, x approaching infinity, okay, what will happen here? What will happen here? Okay. Some students usually making a mistake that making these questions. Uh, so limit or directly substitute the infinity and make it 0. And again, like I said previously, this is cannot be happening because of this is not a number. Okay. So how to deal with the questions? We can write the terms factorize as in like this. Okay. And we can argue that x and x minus 1 become arbitrarily large or really large, okay, and x, and then in conclusion x minus 1 become large too. So we can write this, and this is the correct answer. Okay, okay, I hope you get the idea. Okay, you get the idea. So we can argue and we can have some logical reasoning as your answers. Okay. And also, if you have limit as x approaching infinity, now we can have uh, solutions. If we look at this is a rational functions, right? We have x squared plus x. If we get yes, Helen. Sometimes the question asking the reason, and you need to at least explain the reason. Okay. Okay, let's divide by with x, or multiply with one over x for both sides, and let's see what will happen. So you see here that at the bottom it's going to be less x, right? Less power of x than the top one. This is having the x1. This is actually minus 1, right? If you look at only the variable, okay, you can make a conclusion that this is actually going to have negative infinity. We can argue that because x plus 1, as x plus 1 getting to infinity, 3 over x minus 1 will get to 0. This is going to 0 minus 1, right? So this is 3, infinity is 0. So it's minus 1. So 0 minus 1. So let me just write minus 1. So okay. It's going to be minus 1. So you have negatively large. Okay. Or maybe let me write here. As x is getting to infinity, x plus 1 is going to have infinite, and the other one, it's getting to have negative 1, right? So that's why you have a negative infinity, and yet that's your answer. All right. Okay. I hope you get the idea. Okay. I think I can give you some example. Let me check the question first. Okay, let me give you maybe one or two example more to check whether you understand or not. Okay, let me give you an example. The question is find the limit or show if it doesn't exist. Okay, that's the first one. You can try to check the answer. Okay. The second one is that one more. I think one more. Okay. Okay. I think it's three questions. Okay, Oliver, I just read your question. Prof, can we say that x pursued infinite? It's infinity to infinity side. It's not quite correct because again, infinite is is a difficult concept if you mix up with a number. So at least you need to find out whether you can simplify the other way around. And I think it is better if you look at when infinity divided by -1. Of course, it will be more reasonable to have like you have a positive large number and you multiply the large number with negative. It should be the negative part of that number, right? It's more logical rather than if you have uh, x squared plus x approach to infinity and then 3 minus x approach to infinity. It's not it's not I, I think it will be better if you are not including the uh, or you can elaborate more. Let me explain. Okay, let me explain here. We can say that x squared plus x. We can write the numerator is getting infinitely large and 3 minus x. So as x going to infinity and 3 minus x will be uh, negatively large. But then you have this and this is something that we need to avoid. Okay, we need to avoid. Okay, so it's better if you can at least simplify the numerator or denominator, that will be better, and show that when you have the infinitely large, whenever it is divided by -1 or multiplied with -1, this will turn into a negative large number. And I think that's more reasonable to explain rather than using this concept. Okay.
Okay, thank you.
Okay, back to here. Anyone try? At least the interesting one is the last two. 3/4. Oh, yeah. Not quite correct. Almost correct. Almost correct. I think you need to put square root, right? Because it has square root, right? Yeah, almost correct. Almost correct. Okay, let me show you the number one here. You can try the number two. So number one, we can multiply with 1/x. Let me write down here. Multiply with 1/x. But because it's having the square root, let me put the square root, okay, and x squared. So this will be this is 4 minus 1/x. Okay. And then let me going here, limit as x approaching infinity. Okay, we can see that from the square root, we have 1/x plus 3, right? Okay. And then divide. Let me write a separate limit. All right. Now we can also write down the top one, making it. I'm writing step by step, but you can actually skip some of the process and directly write the answer. But this is just to show you how it's happened. This is 4 minus 0, and the here will be 0, right? This is 0, and you have the 3. So you have square root of 3. So this is the answer. So not 3, but it should be square root of 3 of over 4. Yeah. Stephen, correct. Yeah. Okay, now we have two questions here with some E inside. Let me move this part a little bit down here. Okay. Now how do we solve the second question here? We have E and we have cosine. Okay, remember, okay, every time you get some trigonometric, for this case it's cosine, you need to have, like for example, if you have sine or you have cosine, both of this trigonometric value the maximum is always +1 and minimum is -1. This is also the same case here, right? Okay. So we can say also this cosine x will be in between of -1 and +1. Okay. We can state the first statement. Okay, let's say we start from here. Okay, and then we can argue also that this should be greater than 0 from the graph that we have looked at before. It's always greater than 0 because remember that it never reached 0, right? So it's always at the top of 0. Okay. Okay. So we can multiply this to all of this. Okay. And we can say that this is our inequality. Okay. Now we have three functions, at least, right? And we can use the squeeze theorem, okay, to prove that or to find the middle functions, okay? Because we know that this limit, we write down here, limit as x approaching infinity of this is 0, right? And also limit as x approaching infinity of e, this is also 0. Okay, and that's why as a conclusion by squeeze theorem, this will be also 0. Okay. 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 The third question, it's also include the e. Okay. And the third question, you don't really to calculate or to prove something here. You can use some logical reasoning to answer, okay, because of the cosine. Okay, so cosine. Remember that cosine is always having +1 and -1. Okay, you can actually answer that because cosine 3x always oscillating between -1 and +1. So you can write down it its limit doesn't exist. You can answer like that. And because this is doesn't exist, then the whole limit here is doesn't exist. If you want to make sure that all the limit already evaluated, for example, this is 0, right? So limit x approaching infinity of e to -x, this is 0. But because of this limit doesn't exist, the whole limit becomes doesn't exist. Okay, so whenever you find any limit, okay, and you know that apart from that limit is not exist, then the whole limit become not exist. Okay. Okay. So I hope you get the idea here. Okay. Any questions? Any questions up until here?
Professor, could you help us like graph the? I don't quite understand the 2 cosine 3x do not exist. Could you like elaborate more?
Okay. The cosine, if you look at the graph, it's always like this, right? Let me just write the 2 cos 3x, 2 cos 3x. Because cos have positive 1, negative 1, this will be 2 and this will be negative 2, right? Because 2, because cosine is having plus 1 and negative 1. So 2 cos 3x. So multiplied by 2, it will be 2 and negative 2. Okay. So it's always this between these two number. So can we say it's reaching a finite number? No, right? Because it's always oscillating. Okay. So because it's always oscillating, we can say that it never have any limit. Okay. Unless uh, if you have a graph like maybe first is like this, and then it's getting smaller, 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 and we can say that probably this is the limit, the middle here. Maybe that's the limit. It's getting closer to this line here. It's also oscillating, but it's oscillating and then getting closer uh, to a finite number. Whole graph, which graph? The cosine. Yeah, if you are not really sure how to draw, you can practice with the GeoGebra. You can practice with the GeoGebra. Let me show you. Okay, that's the graph. Okay. 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 So yeah. So it doesn't have any limit, right? So it's always getting to positive 2 and then negative 2, right? Okay, I hope you get the idea here. Yeah, I think you can also check uh, with your laptop, like the GeoGebra. So whenever you find any interesting function that you want to draw, you can go to GeoGebra and then uh, you can take a screenshot or just download the image if you want, and then put it in your notes. If you're using digital notes, you can put it and then make you write some notes from there. I think it's helpful. I think GeoGebra also have the apps in a smartphone or tablet, but I'm not sure how good it is compared with the web. You can check also. Let me write. The other one is complete today. The other graphing calculator also can be looked for. So you can also try Desmos or GeoGebra. But I prefer GeoGebra. I prefer GeoGebra, but you can also try Desmos. Okay, let me go back to all right. So let me give you some quick review on limit at infinity. Okay, based on precise definition of limit. Okay, so precise definition of limit, you need to include an epsilon that is to indicate a small fractions in the graph. Okay, so if you look here, the definitions. Okay, this is a definition of limit that you already know for limits at infinity, and then you need to have an epsilon, a positive epsilon. Okay, that has a number n. Okay? So number n is just to indicate, okay, just to indicate when x is uh, approaching infinity, the value should be always greater than n, the corresponding number here. Okay? So n is it can be any number, okay? And then the distance here is always uh, less than the epsilon, okay? Or the maximum distance here should be the epsilon here. And also when you have the n here, okay, when x is going to have an infinite number, this is to say that the uh, the the f of x is always nearby this area here. Okay. Okay. And similarly, when you are going to the left side of the graph, going here, you also have the n, and since it's going to the left, so x it should be less than n. Okay. And it can be any number. Again, it can be any number. And the important thing here is the distance here should be the epsilon. This is to show that whenever you're moving the x, okay, whenever you move the x, your solutions or your value of f of x, it should be around here. And remember that because epsilon is very small, this is just to show you that it has a limit, okay, which means the uh, the f of x is not equal with is not necessary to be equal with the, or I mean, this is not correct here, not necessary, or limit xa necessary to be equal with the f of a, or in this case, when x is getting infinity, it should be equal with L. But of course, if you want to find the value of infinity, it won't be possible, right? But we can look at the graph when we have the infinity, or in this case is negative infinity. We will have some value L here. And to have some good definition, we need to have a certain number n at which the x here, because it's always in the negatively large, it's always less than this n. So x should be less than n. Okay. So n is just like just to show you that the x is getting negatively large, and at the previous one, the x is always greater n. This x is always greater than n. To show you that the x is approaching to infinity. So n it can be any number that large, and x is always greater than n. Okay. And of course, we have infinite limit at infinity, what we have done before. So in precise definition, there will be an m and n. Okay, so n will be for x. So as x is getting larger here, so let's say x is getting here, it's getting infinity, you have also m that is going to be infinity. Okay, or maybe to be precise, is f of x is getting also infinity. But of course, this is in terms of limit. N and m is just a parameter, just evaluations that showing the x always getting larger, and f of x becomes larger too. Okay. Okay, I think that that's just a slide, a definitions to help you understand better. But I think you don't really need that precise definition for solving most of the problems. The intuitive definition is already enough definition. But of course, in mathematics, you need to have a precise, like the limit, uh, how close it is, right? Then in precise definition, the closeness, the, the symbols, we have the epsilon and delta. If you watch my additional lecture for the epsilon and delta definition of limit. Okay, so this is just to show you that there is a small gap to show that it's close to certain value. Okay. All right. I think I forgot to mention one section in the 2.5 actually. Last part of 2.5. There is a theorem called intermediate value theorem. Let me write the official theorem, and let me use the theorem in some examples. Suppose f is continuous on closed interval. Let's say we have interval a to b, closed interval, and let n be any number between f of a and f of b, where f of a is not equal to f of b. Then there exists a number c in AB such that let me write in FC is equal n. All right, it's it has some words here, but I hope you get the idea. So suppose the functions f is continuous on closed interval from a to b, okay? And let n any number between f of a and f of b, where f of a is not equal f of b. Okay? And then the conclusion will be there will be a number c in the interval ab that when you evaluate c in the functions, it will be equal with n. Okay? I think if I draw this, it will be much better. Let's just write, or maybe like that. Okay, and maybe this is A, and this is B. All right. Let me use the color. And this will be f of A, and this will be f of B. Okay. And maybe we have C here, and this will be our n. And this is showing that the f of C is equal to n. And then the question is, how do we use it in maybe some cases? Okay, let me give you cases. Show there is a solution of equation let's say we have this cubic formula here, cubic equations. Okay. We don't really need to find the solutions, but we need to show there is a solution of this equation. Or maybe adding between 1 and 2. It's already giving the interval between 1 and 2. Okay. Now to look the question here, we will have some function here. So let this become our function. We need to find a number c. C is between 1 and 2. And when you have c, it should be equal with 0. All right. And then we can take the a. This is a, and this is b. And we can evaluate each number. So it will be 4 minus 6 plus 3 minus 2. It should be negative 1. Okay. And we have f2 is 4x 32 24 plus 6 and minus 2. This is positive 12. Okay, now we see that this is a negative, right? This is negative, this is positive. You can write down that f1 is less than 0, less than f2. So we can say that because it is in between f of a and f of b, or f of 1 and f of 2, we can say that there is at least one solution or number C between 1 and 2. Okay. So it doesn't really necessary to find the solution, okay? Because the question is just to show there is a solutions for this equation. Okay. Okay, that's the intermediate value theorem. Okay. Okay, maybe let me add like illustrations for the functions. The functions is I don't really care how the functions will be, like, but I know f of 1 is negative, so maybe f of 1 here and f of 2 is here, right? The solution of the function for the cubic, it should be at the 0 here, right? So the idea is that if I have a point here and then another point here, I don't care the middle part, how it looks like, because the question is not required me to look for. Okay? But I know that from this point here, is A and B, I need to move across this, right? Across this, right? So that's why it should be having the C here. Okay, so from here, when you get this is negative and this is positive, you already get the proof that it should be crossing this x-axis. And then you got the proof that, okay, you have at least one solution. And the solution itself, we don't really sure what number, but we know that there exists one solution here. So here exists at least one solution. Okay, that's how you're visualizing. I think it's better with the graph, right? It's better with the graph. So you can look that this is crossing the x-axis rather than using this and then you don't really sure what you are going to do here, right? But if you look at the graph and you know that this is negative, this is positive, of course, there will be a number in between that is crossing this x-axis, which is the solution itself. Okay. Okay. Let me move to the next part. Okay. We'll move to the next part. Any questions first? Any questions? Okay. If not, let me go to 2.7. This is the 2.7 derivatives and rates of change. Okay, so because next Monday holiday, we still have a Friday class still online. Okay, and maybe after that we will have physical class, but let's just wait for the announcement from me. Okay. Okay, so derivatives. To begin with, to understand the derivative, let me see the let's observe the graph here. Okay. Let's have a random function. Okay, a random function f of x, and we have 2 points P and Q, and let's connect that 2 point, and we have a secant line here. Secant line. What secant mean? It's mean to cut a line, to cut a curve, and connecting two lines. Okay, to cut it's a secant line, and then we have a number a here and x. Okay, and of course we have point b a and f of a, and point q x and f of x. Okay. And then we can also see that it's creating a triangle here with fx minus f of a and x minus a. Okay. Okay. Now, of course, you're already familiar with the slope. Okay, from the picture, slope of PQ is the delta y over delta x, and you can write in terms of wait, you can write in this form. Okay. Okay. Now we want to know the tangent. Okay. I think I've given this similar graph in the early class when we discussed about limit. Okay, let's imagine. Okay, from this curve. Okay, imagine what you have the point Q is moving. Okay, moving to the left, okay, moving along the curve. Okay, so the Q is moving along the curve, and eventually this Q here will getting closer to P. Okay, so you have, let's say this is X here, and this is A. So your X here is moving, approaching number A. Okay. So when approaching number A, we can also write the gradient then, let me write in here. The gradient then, if we approach x to A of f of x minus f of A and x minus A, this will be the tangent line. This is at point P, A and f of A. And the slope, or let me write, with m as slope is this. Okay, so what does it mean actually? Okay, so look at this line here. This is the secant line of PQ, right? So when one of this P or Q getting closer each other, let's say the Q is getting closer to P, okay, the secant line then it's getting closer to a tangent line at P, right? See that the line, okay, the line here, first is like this, and then it's like this, and then it's like this, and maybe in here it's like this, maybe here it's like this, right? And eventually it will going to be getting closer to this tangent of P. Okay, tangent means, okay, if you don't remember, so tangent means if you have P here, the tangent is the line that touch uh, at exactly one point. Okay, or maybe if I draw more clearly, it's really, yeah, it's not really uh, clear here, but what you need to point out is it's touch 1 point, precisely 1 point. What that's the tangent means. Tangent means to touch. Okay, because of the pixels, you cannot really see that it's 1 point, but in reality, the tangent line means it's touch 1 point. Okay, so the P here, the line here is touching point P exactly 1 point. Okay, and the slope is basically a limit as x approaching a of f of x minus f of a over x minus a. Okay. Another form that maybe some of you more familiar with, we have this form. Okay, so we have, instead of x, we now have a plus h, and we have the distance is h. So you have when you move q, when you move q to the here, then the distance from h is getting smaller, right? And it's getting closer to 0. And you can write that limit as you can write that as your definition for the slope. But it's actually similar with the previous one, but it's just a different form, different formula. All right. As I mentioned before, now it's 9:50. So I think I will keep this for our Friday class. This picture for reviewing the in terms of velocity for the rate of change. Um, we will have now our feedback time. Okay. So please, if you have, if you have pen and paper, I think you can prepare that. Because I think there is some calculation that you need to write. So please go and scan the QR code. Okay, if you have trouble to join, let me use the other screen. Okay, wait a moment. So this will be an overview for several section on chapter 2. Okay. Okay, I will wait for a few seconds. Okay, 32, 33. All right. 57. Okay, you can use the website if you cannot join the QR code. Okay, I can start now. Okay, get ready. Okay. Okay, ready? I will enter. Okay, 40. Okay, anyone join? Okay. You can use any nickname, but if you win the game, please tell me your student ID. Okay. Okay, 41. I think one more. Okay, 42. Okay, let's start. 3, 2, 1. Let's go. And you need to find the false one, the wrong one. Okay. 20 seconds. 19. 5, 4, 3, 2, 1. Okay. Thumbs up. Whoa, okay. Yeah. For E, you need to be careful. There is continuous from only one side, right? So that's actually true. The false one is D. Okay. You guys ready? Okay. Yeah, magical rhino. Okay. If you win the game, you need to give me your student ID. Okay, the next one. Question 2. Get ready. Let's start. Okay, that's the question. And you need to type the answer. You need to type the answer. Type the number if you find the number. Yeah. Yes, I think you need to write something if you want to check. Okay, 5, 4, 3, 2, 1. Yeah, just answer with anything with random answer. Oh, good. It's 1. Okay, it's 1. All right. Post correct one. Yeah, all we will be getting 10,000. I had 10,000. 1,000. 1,000. Okay. All right. Oh, good. Last question. Okay, 3, 2, 1. Let's start. You need to answer fast if you want to get more points. Okay, true or false? I think it's quite easy if you remember what we have uh, done before. What happened when you have a limit? Okay. Okay, good. Good. It's true. So whenever you find in a part of the limit it doesn't exist, its whole part will be doesn't exist. Okay. Who's the fastest? Oh, oh, Sandy, you are the winner. Okay, congratulations, congratulations. Okay, okay. Last question. Actually, this is not a quiz, but this is just I need your feedback. Like, when do you want to have a physical class? Maybe as soon as possible. Maybe November. Maybe October, or maybe late October. It's also fine. Oh, why you are answering online class all the time? Whoa, are you sure? Oh, do you have any reasons why you want to have online? Okay, most of your answering. Yeah, yeah, yeah. We can do physical and online. Yeah. All right. I will make an announcement very soon, but next week still online. Okay, next week still online. So Friday next week still online, and after that, wait for my announcement when we will have a physical class. Probably in the middle of October, or maybe third week of October, probably. Okay. Just wait for my announcement, and this is the end of the class, so you can leave the Google Meet. Okay, if you have any questions, you can ask. Also, if you don't have any questions, you can leave the Google Meet. Okay. Okay, yeah, you're welcome. Okay. See you soon, international students. I will wait for your coming to Taiwan.